Okay. So the reason I'm asking for your number is that Gradescope actually detects your name and tries to tell us to match it to somebody in the class. But you guys can't write worth a darn. I got to tell you, some of your handwriting is really pretty scary, and mine's bad. So when I say it's bad, it's really bad. Please write clearly and use good numbers when you write your ID number, because if we can't read your name, at least we'll get your ID number. Okay, that's kind of it for the exam. We're going to look at, and we will have class on Friday. Of course, it's recorded. I know some of you are anxious to go to spring break, and I get that. But the class will be recorded on Friday. Probably we'll go over the exam solutions on Friday, I would guess. We may do a little bit more work on our word ladder game. We'll see. But there will be class on Friday. Okay, so in Lab 6 tomorrow, and also on the exam on Wednesday, there will be problems that require recursive solutions. And I thought it would be good to pause for a moment in our word ladder thing and actually do a problem together in class where you construct a recursive solution. So this is sort of extra off the record, sort of off the regular flow of the class, but I thought, given the questions I've had, I thought it might be worth doing. So here's a problem. It's called flatten. It asks you to take a list L, which may be nested, containing integers. So the list could look something like this list. The first element is a list with one element, which is a list with one integer in it. The second element is a two-element list. So it's a list or a nested list of integers. And what we want to return from this is the flattened list of those same integers in order. So basically, I want to get rid of all the nestings and raise them, elevate those into a flat list with just one list. Does everybody see what the problem is? Pretty straightforward. So let's talk about how we would approach this kind of problem. Clearly, given the input that looks like this, I sort of have to be able to descend into that nested structure and pluck out the element that I find there. Whether that's a single element like there is here in this deeply nested list, or more than one element as it appears here in this less nested list. So I'm going to sort of have to descend and then elevate them and concatenate them together. So we can see sort of that the recursion here is elevate this element so that it's a list of one element, and elevate these elements so it's a list of two elements, and then concatenate them together. Now notice, this says here that we're returning a new list. We're not modifying the list. We're creating new list structure. So normally I would say, let's use a comprehension. But here the problem with the comprehension is that I can't really do this kind of deep descent kind of thing nicely in a comprehension. So I'm going to use a different form of iteration, which I'll explain in a minute. But fundamentally, the idea is going to be solve this part, and concatenate them together. So I'm going to posit that my recursive step is going to look something like this. I'm going to take the first element of L, and I'm going to flatten it and get back something that's probably a list, which I will concatenate with the rest of the list flattened. Now, if you think about this, in a sense, I'm peeling off the first element and returning a list containing all the numbers therein. And then I'm going to do the same thing for the rest of the list. So this is, we think of this as the head of the list, and this as the remainder of the list. For this reason, this is sometimes called tail recursion, because I have the head and the tail. I'm going to do something to the head, and then I'm going to do the recursion on the tail of the list. Here I have to do recursion on both of them because the head might be deeply nested as well. So as I look at this formulation of the recursive step, I notice that because the whole thing returns a list, where does it say? Returns a new list, and I'm using concatenation to create the new list, that means that flatten here and flatten here must also return lists. So I already know some things about my function. I know that the recursive step is going to do something to the first element and then do the same thing to the rest of the elements. That the recursive call to flatten, and indeed every call to flatten, returns a type list. And then I'm going to take those types and I'm going to concatenate them to get new lists that I return. So let's take a look at what I might look like. So here's my skeleton for what my recursive function looks like. It's a call to flatten, and I've already talked about the recursive step, so I'm going to stick that up here right at the end in the else. And I'm going to have some sort of if structure because I know from class that a recursive function has one or more base cases and one or more recursive step, right? Where the base cases are what we use to sort of stop the endless recursion. And the recursive step is how I partition or unpack the problem to solve it in parts. The whole idea behind recursion, there's an idiom to this. It's called divide and conquer. I get a big problem, I'm going to break it up into little problems and keep breaking it up until I can solve the simplest possible problem. And then I'm going to suture together all the solutions to get the solution to the largest problem. This is the whole idea behind recursion. Big problem? Well, let's break it down and unpack it until I get a simple problem where I know the solution is what it is. And then I take all those solutions, return at the simplest layer, and as I back out of the recursion, I suture them together. We saw examples of this where the backing out and suturing was just addition. Here we're going to see an example where the backing out and suturing is structural. It's a list. Now, the fact that I said there are two base cases here, I don't know how many base cases I'm going to need. There can be one of them, there can be more than one of them, but there has to be at least one, or I'm writing a recursive formulation that will never end. It will never stop calling itself. And what do I know about these base cases? What I know about the base cases is they don't invoke flatten. Now, in some recursive functions, there may be more than one type of recursive step. We've seen that in binary search, right? There's a recursive step that goes to the high side and a recursive step that goes to the low side. But here, as I build up structure, I've sort of handled the whole list, either as a single element in the head or the remainder of the elements in the tail. So there is no other recursive step here, just one. Any questions so far? Does this kind of make sense? Does it evoke to you binary search? In binary search, we partition the list into the below the midpoint and above the midpoint, and then we go down one or the other. Here we're partitioning the list, but we have to go down both sides and then suture them back together again. Questions? All right, so base cases are what keeps the recursive step from generating an error or stop the recursive unpacking process. So let's see what these mean. Well, in the first case, I have here, take the first element of L and flatten it, and then take the rest of the elements of L and flatten it. What error might I generate if I'm not careful? How would that break? Is there an L that would cause those to break? Anyone? What list do you know? Yeah, go ahead. So if L only had one element, then L0 would have a value. And L1 colon would have a value as well, but it would be the empty list. So what's interesting about the one element case is that when I recursively call L on the empty list, the next time through flatten, L0 will not have a value, and I'll get the error case I'm talking about. So my worry here is if the list is empty, this will break. So the first thing is, if the list is empty, you can't break it up anymore. It's sort of the base case, right? Empty list, nothing you can do about it. And the second case is that if this element is not itself a list, I will invoke flatten on, say, the number 7, and then I will try to find the first element of 7 and I'll get another error. So I know that there are two cases that are a problem. One is when the list is empty, and the other one is when the thing is not a list. So I can't flatten the list I can't take the head of the list if it's empty, and I can't flatten an integer. I can't unpack the integer. I can't break it into L0 and L1 colon. Now the second one, the integer part, requires being able to test if an element is of type list or of type integer or whatever. So we have to talk about that a little bit. All right, so let's remember my structure here. Let's start with the first case. Checking for the empty list is easy. How do I check if something's the empty list? Well, that's simple. I just check for equivalence to the empty list. So I change my condition. If L equal empty list, Then I'm going to do something. What do I do? What is the flattened version of the empty list look like? Forget about all the recursive stuff. Remember what flatten does is it takes a nested list and returns the unnested version of that list. What is the unnested version of the empty list?
Would it be none?
Well, it wouldn't be none. It would still be what? Still be close, same type. What does flatten return? What type does flatten return? A list. So what's the flattened version of the empty list that's still a list? It's the empty list. The empty list is flat. There's no nesting in it. This list is already as flat as a pancake. What is there to unpack? The answer is nothing. So what I want to do is I want to return L, which is the empty list. Think about it. If I invoke flatten of the empty list, what is your natural expectation for the result? The empty list. It's nothing nested. The task of flatten is to elevate all the elements so that they're in a one-layer list. Well, if there are no elements, there's nothing to elevate. You're still back to the empty list. The second case here is when this thing is not a list, but is something else. We only have lists or integers here, so the something else is an integer. So I need to check if the type of the element is not a list. I have a problem because if I get to this case, I'm going to try to take that first element of something that is not a list and I'm going to get an error, which I don't want. So I need to check if that element is a list or not. So I'm going to check for listness, being a list. We could as easily check for integers and just say, is the thing an integer, then do this. But by checking for lists, I allow for my flattened list to contain even floating point numbers, for example, or characters, things that aren't lists. So the more general version is just to check, would seem at least, to check for lists. Notice that the specification doesn't tell you. It's a question you would ask. Or if you don't know, you just make an assumption and say, I'm going to assume that it's more important to check for list than for integer. So one way of checking for a type of an element is to say if type of element is whatever the type you want. So if type L is list, or you can just say type L equal list. So we can try that on for size. Here I'm going to check for not list. So if type L is not list, that's one thing. I could say type L not equal list, not bang equal sign. Could do that as well. So that's sort of the easy way of doing it. The other way of doing it is to use a function called isInstance. It says isInstance L comma list. It returns true if it's a list and false otherwise. So it's a Boolean. That looks like this. I'm going to go with this one. I actually like isInstance better, but this is strictly personal preference. You can do either way. Now what happens if the thing is not, sorry, this should be not isInstance list, right? Type L is not list should be not isInstance list. So, what happens if L is not a list? What should I do? Well, the answer is, I want to return whatever I had as L, let's assume it's an integer, in a way that I can concatenate it, I can, add it or concatenate it to other parts of my growing structure. Since I'm putting together a list, returning the integer and trying to concatenate the integer with a list is going to break. So I need to return a list of one element containing that integer. So in the first case, I just return the empty list. In the second case, I return the list of that integer. And that would give me a list here, plus presumably the flattened version of a list here. And I would concatenate those together. So we can see that, in fact, this solution takes a list that is deeply nested and returns the flattened version of the list. Now, I apologize for the isInstance here. It should be not isInstance, don't forget. I did get the not type version right, but I was typing quickly this morning, so got carried away. Does everybody understand how this works? The key insight is, how do I partition the structure that I'm recurring on? Give you a recursive structure, or nested structure you have to take apart. How do I break it up? Typically, one of the most common ways of doing that is that you do something to the first element of that thing, and you do the same thing to the rest of the elements of the thing. Notice how the first thing descends into the structure, and the second part iterates over the structure. So this is a combination of an iteration over the structure with a descent into each successive element of the structure. And then you put it back together. Questions? Now, you've seen binary search, which has this kind of nice logarithmic behavior. You've seen a version of recursion here that does a form of iteration, this head and tail part, combined with a sort of a recursive descent part in the head. This is the most common recursive idiom. It's the one that you'll see a lot. And it's one that you should be familiar with for the lab tomorrow. It'll help you. Yes?
I missed the writing on the first checking type element.
So here, this one is actually correct. It checks if the type of L is not list. And then the next one, which is this instance, I erased the not. I shouldn't have erased the not. I should have just left the not. I apologize. Okay? So where were we? We were building our word ladder game, which we won't finish before spring break, but we'll finish shortly thereafter. And we talked about how the word ladder works. We talked about the general approach, which is to build a graph of words, where each word is a node in the graph, and words are linked with an edge if they differ by one and only one character in the word. And we started out by writing a rneighbors function that takes two words of identical size, iterates over the word itself, the length of one word, which they're both the same, so it doesn't matter, and checks each element to see if they're different. If they're different, I increment my initial count of 0 by 1, and I return true if count is 1 and only 1 when I'm done with the iteration. We saw that this works. Cat and hat are neighbors, cat and dog are not, and so that's fine. Then we talked about how I would actually take this function that I developed in the read-eval print loop, or perhaps in a buffer, and put it in a file for a larger piece of software. And the answer came out to be something like this. The header, the comments at the beginning were used to give the specification of the function, just like you've seen in every question of the day and every homework assignment. And then there's some other interesting things that are going on in the function that you may not have seen before. The first thing you'll notice is that there are embedded comments with the hashtags in the body of the function, indented at the same level as the code. And these comments are meant for the obviously human reader that tells me something about the next statement. So for example, here it says, return true if only one difference was discovered. That explains why I'm returning count equal 1. It gives the human interpretation of what that means. Here I give a human interpretation of what I'm doing. I'm stepping through the words and counting mismatched characters. That's what this loop does. So it breaks the code up into chunks that let me understand what my design decision was when I made this function. So we've been working a lot at the implementation level, but we haven't done a lot of work at the design level. So we're going to be doing more design now, meaning that I give you a specification, and you have to come up with an algorithmic solution, which may involve multiple steps, and it's good to document those steps as comments. Now, in homework 1, we don't do this, but in subsequent homeworks, you'll be asked to comment your code, and the quality of your comments will be part of the grade. So it's part of the style grades you get. Did I put adequate number of comments? Are the comments helpful, or do the comments get in the way of the code? The last thing you'll notice here is this funny string right after the signature with triple quotes. And there's two odd things about that. One is that I've got a string in line in my function, which doesn't make a lot of sense because evaluating the string returns the string, which then that value doesn't seem to be used for anything. So that's one thing that's odd. And the second thing is, you've seen single quoted strings, you've seen double quoted strings, but now we have a triple quoted string, and what is the meaning of that? All right, so the lead comment describes the function's specification. And then there's that extra string literal right here. Now, this string literal, meaning a string literal means just a string. This string after the signature occupies a special place in Python's definition. And it actually is the string, the text, that informs Python's help function. So let me show you how this works. It's called a docstring. And when I'm in the read eval print loop after I've read in RNeighbors, I can use the special function help RNeighbors, and Python itself will say, here's the help here's what I know about RNeighbors from the main module. I know that RNeighbors has this signature, and it returns true if W1 and W2 differ in exactly one letter. There it is. That's that text verbatim printed out as the result of my asking for help. So as you write your Python code, if you've forgotten what the argument order is in a built-in function, say isInstance, you can say to Python, help isInstance. And it will tell you, because all the built-in functions have this docstring, it'll tell you what isInstance expects in terms of parameters and what it actually does. You can do this for your own functions, but not if you don't put a docstring in there, because it'll just say help RNeighbors and say, I don't have anything to tell you about that. It doesn't have anything. So good code will contain a docstring that helps the coder, when they're in the read eval print loop, ask questions about the function itself. Are we clear on this? Does it make sense? So this is part of that really careful process of writing your code. It's good to document as you go, both in the file that will be loaded, but also so with documentation that can be accessed from within the software system. Now, the second part that's unusual about that string is the triple quote mark. And let me tell you about the triple quote mark. So the triple quote mark is what's used for what's called a long string, and a long string can span multiple lines. So for example, if I type to the REPL, triple quote, this is carriage return, attest, carriage return line, carriage return, and so on, you'll notice that the read eval print loop provides those ellipsis dots to say, I'm still waiting for more input. You've probably had this happen to you when you forget a closing parentheses. But it's also the case when you don't have a closing quote for the string. So the triple quote says, I'm going to accept a string and it can have many lines. That means that your docstring, the help you give, can be a little paragraph, paginated just the way you type it. What does the string look like when you evaluate it? Well, you get back a single quoted string, but notice the explicit line feeds, \n's embedded in it. And if I print it, if I were to print this string, I will actually have these \n's evaluated, and I'll get back the string exactly the way I type it, spanning 6 lines of text in the REPL. So you've learned today about docstrings. You've learned about triple quoted strings, triple quoted quote, and then we had that little excursion in the recursive function. So why not a comprehension? Well, we know that W1 and W2 are the same length. So we actually could do this with a comprehension. We could say, collect true if I in range length of W1 with a filter expression that says if the ith element of W1 is not equal to the ith element of W2, collect true. If they are the same, you don't collect anything. So this comprehension, perfectly reasonable comprehension, will have length 1 if and only if the words differ in one character alone. And then I could take the length of this result and check it against the number 1. So that's a nice, concise list for RNeighbors. Unfortunately, it actually builds you a structure which we immediately throw away. Now, it's not a big deal to build a list of size 1 that you throw away. That's not very wasteful. But it does kind of go counter that sort of organizing principle of iteration that you use comprehension to build structure you're going to use. Here that structure is volatile. I build it, I throw it away. It's incidental to the computation, not central to it. So not everything needs to be a comprehension, and indeed here, words are short, so it doesn't really matter much, because there are only 5 letters wrong. But I'm also missing an opportunity to have an iteration that exits early. So let's just for a moment imagine that the words, instead of being 5 characters long, are 100 characters long. And I only allow them to differ in one location. And you can imagine stepping through those 100 characters, checking character by character, and you find a character, say the 5th character doesn't match. And you go on and you find that the 6th character doesn't match. Well, at this point, you already know that the 2 words are different because they've already differed in 2 locations and you still have 94 of them to check. But whatever happens in those 94 other locations is not going to change your answer. You've already had 2 failures. You're done. With the comprehension, you'd still build that whole structure just to count to see that it was equal to 1 in length when it exceeds 1. You already know it's going to exceed 1. But if I use a loop, I can actually check. This is my same function, same docstring, but notice the difference. I start with a counter at 0. I let I range over the length of the word, so 0, 1, 2, 3, right up to 4, which is the length of that word, which is 5. If the 2 characters are different and the count is already 1, means that this is the second difference I find, I'm just going to quit. I'm going to return false. Just, I'm out of here. There's nothing good left to be done. Tiny little incremental improvement in performance for words of length 5. A possibly meaningful improvement in performance if you do this many, many times on longer words. Otherwise, if the count was not already 1, I'm going to increment it by 1 here. And at the end of the day, I'm going to return true if only 1 difference was discovered. Now, this structure can be further modified because you'll notice my counter really only has 2 values now. 0, meaning I haven't found a mismatch, and 1, meaning I have found a mismatch. So I could even get rid of the counter and just say, make this a variable like x and say x equals false. And when I hit the difference, I can set x to true as long as it's not already true. If it's already true, I just exit. So there's a lot of things I can do here to make this, cleaner or simpler or whatever. But basically, iteration here in the form of a for, because it's bounded, is the way to go. And my code in my function looks something like this. In my file, looks something like this. There is a header, which is the specification, my docstring, and so on and so forth. And you'll notice that here, one of the nice things about IDEs is that they colorize your code. And I assume all of you are using an IDE that does this. But colorizing code is important. It's important because your eye is very sensitive to variations in color. And if you had done something like forgotten a parentheses or had a missing quote to close a string, it wouldn't look right. You would be able to tell right away that the red of the string continued into your code. And it's the most visible clue, that sort of visual clue of the syntax being wrong can help you be more effective as a coder. Questions? So this is our first function of our word ladder program. Now I'm ready to use this, but to use this, I'm going to have to read in that dictionary of words that I have in that file. Remember, I have 5,757 words, 1 per line in a file, all lowercase, all 5 letters long. So our next challenge is loading my code and reading the words from a file. So let's see what I can do. So my code is stored in a function called WordNet, or in a file called WordNet. And I import from WordNet, I import star, which means give me all the functions in that file, load them in, and put them in my main module so I can just use the names directly. With your homework 1 file, you would say from homework 1, import star, and then you would type play with the arguments you want to play. I can do help our neighbors like I've shown you before. That tells me that our neighbors is in fact imported into Python and is available at the top level. I'm ready to go. So let's read in some words and see what we can do with those actual words from my word list. So there are a couple of ways to read stuff from a file. The first step, however, is that I need to open a handle into the file. What does that mean? The file is a structure on disk, just a bunch of bits on a disk that your operating system is managing. Whether it's Windows or Linux or Mac, your operating system knows that this file exists, has this name, and it's located on the disk in this location. We need to tell Python, we need to connect that file, that specific file, to Python in a way that it can reach in and pull stuff out of that file. We say that the process we're using is something called creating a file handle, and we do that with the function open. So let's talk about this open function. So open takes a first argument, which is a string, which is the name of the file. So my file with my words is called words.dat. It's in quotes because it's telling it that this is a string that corresponds to the name of the file. That file, by the way, the operating system is going to be asked, can you find this file for me? And the operating system is going to look in the directory where I invoked Python. So that file has to be available in the same place that I invoked Python, which is presumably the same file where my wordnet.py file is located. Those of you who have trouble opening files, the single biggest problem you will have is that you're asking to open a file that the operating system can't immediately find in the location you are currently running. Every running process is running in a location on your disk. And if you just say open words.dat, it's going to assume that file is located there. If the file is located elsewhere, then this string is going to be a much more complicated expression. It's going to start with, on Windows, C:, and then a path name to the file, for example. In Linux, it will start with a slash and a path name to the file, presumably the same kind of thing in the Mac. So these are all sort of operating system specific changes. The second thing you'll notice is that the open function not only takes the file name, but takes what's called a file mode. And this mode here asks me if I'm opening the file to read from it, or if I'm opening the file to write to it, or if I'm opening the file to append to it. Now for now, we're not going to be writing anything to this file. We're just going to read stuff from it. So I tell the operating system, I want access to words.dat just to read from it. I'm not going to change it. Just want to know what's in it. This function returns an object, an instance of an object, called a file handle. And I can use that object. It comes with a bunch of methods. One of them is the read method. So the simplest way to read from a file is to create the file handle, the object that represents the open file, and then invoke the read method on it and assign the input to a string S. Simplest way. What this does now is it reads in the entire contents of the file. All 5,757 words are in a big string, which we called S. And that's great if the file is not too big. So let's take a look at the length of S. Well, the length of S is actually 34,542 characters, which you'll notice is 5,757 times 6 minus 1. Because why? Because it's 5 letters plus a space or a line feed, and there's 1 fewer line feeds than there are words. So let's look at the first 20 characters, and you'll see that my words.dat file has those 5-letter words arranged in alphabetical order, separated by a new line character. So each word is 1, 2, 3, 4, 5, 6 characters, except of course the last word, which may not have that line feed. Actually, I think it does have the line feed, so it's exactly divided by 6. 2 for 6 and 9 and 3. Yeah, this is divisible by 3, so it's divisible by 6, so it's 57 times 6. There's a trailing line feed in my file. So I can use all the string methods on S. It's just a string. I can split it, and I'm going to call this new variable W for the word list. The length of W is 5757. It has split the string on the only white space character in it, which is the new line. New line's like a space. It's white space. And if I look at the first 4 words, well, there they are. Okay? So I've started with the open command. I've told the operating system where the file is. I've opened a file handle saying read from this file. I've used the file handle's read method to read in the whole file all at once. That gave me a string with the contents of the file in Python. I can break the string up with normal string methods, and I get my list of words. Sound like a plan? Everybody clear on this? Easiest way. We're going to do this 3 different ways. This is the easiest way. And finally, because I'd opened the file to read, and I've read what I wanted from it, it is good practice to close the file handle when you're done with it. It's like when you reach into the underwear drawer in the morning and take out a clean pair of underwear, you don't leave the drawer open. You shut it, right? It's just clean up after yourselves. Programming is a lot about manipulating structures, but you also have to keep your environment neat and clean. Minimize what you leave lying around. Here's another way I could do it. If my file is really big, meaning on the order of the memory I have in my computer, I don't want to read the whole thing in one step. Maybe I want to go through the file and find a particular word. I don't need to load the whole 100 million word file into Python just to see if the word is there. I might want to look at each word one at a time. So we're going to modify this approach. Instead of reading in the whole file, we're going to read in a little bit at a time. It starts the same way. I'm going to open the file again for read, and it's the same file I'm opening. So I have my file object again, the file handle in file. But now, instead of using the read method of that file type, I'm going to use a method called readLine. And what readLine does is instead of reading in the entirety of the file located at in file, it's going to read in one line of it, right up to and including that carriage return. So if I look at S now, I'll see that it contains the first line of the file as a string. Now this carriage return or new line character is a character. We've seen this before. It's the type of character that fits in the class of characters known as white space. So we've used the split method of strings, which takes an optional argument. It says split the string using this character as a splitting character. If you don't give an argument, the default argument for split is any white space character. So a space, a new line, a tab, all of those are the dividing space. That's why we naturally get lists of words when we split a string, because words are separated by these white space characters. You can split on anything you like. You can split on commas if you're reading comma-separated value files. That works fine. But the default version of split just splits on white space. So here, I'm not going to split this because I've got my word already, but I do want to get rid of that extra white space. So what I'm going to use is, instead of split, I'm going to use a function called strip, or a method called strip. And moreover, as a method of this file object, readLine returns a string, and strip is a method of string. So I'm just going to append that dot method notation to apply strip to the result of this readLine. And what strip does is it looks at the string, and it tries to trim both ends of the string, removing characters that are white space characters by default. Like split, strip has an optional argument here. We're going to let it default to white space. So if I do that, I'll see that what I get is the word, but without the new line. That's one thing I notice. And the other thing I'll notice is that if the first time I do readLine, I get the first word. The second time, I get the next word. So this object contains state in the sense that every time I hit it and say readLine, 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 it not only returns the line to me, but advances the pointer. In a sense, this readLine function acts like a generator, which we've seen briefly in class. And by the way, avoid generators unless you really know what you're doing with them. There's a couple of students who've gotten really sort of caught up trying to write comprehensions and forgetting that a list comprehension needs square brackets, and a dictionary or set needs curly brackets, and if you don't put any bracket, you get a generator, which is not what you think it is. It's going to cause you trouble. So this is a generator in a sense, because every time I call it, I get the next thing out of infile. Again, I can close the file at any point in time. So that's my second solution. Either read in the whole thing, solution 1, read in things one at a time, solution 2. And let's take a look at solution 3. Again, starts with an open file, just like before. Notice that every time I open the file, it starts reading from the beginning of the file again. I'm going to initialize a list, W. And I'm going to write a little for loop that says, for line and in file. So here I'm going to use iteration over this object. This object that represents a handle into the file is an iterable. That means that it can appear as a sequence object in a for loop. So every time I say for line and in file, the fact that I'm iterating over in file, the natural iteration is by line. So this form adds a whole lot of default meaning. There's no use of the word read line, but that's what it's naturally doing. And what I'm going to do here is for every line in that in file, line will take on successive lines in the in file. I'm going to strip that line and I'm going to append it to W. The length of W then is 5757, and the first 4 words are my words in W. Now, these forms are all related closely, and they're all kind of do the same thing. The difference is in their behavior. The first one reads in the whole file, which may or may not be desirable. The second two access the file line by line. One under explicit control of you. You can do the same kind of thing with a while loop and the other and a read line embedded in it, or you can use this sort of natural syntactic sugar that treats infile as an iterable object and iterate over infile and get the behavior that you want. All 3 forms are kosher. Okay. All right, so this is for reading text from files typically. We'll talk about other methods later. You use any one of these. Remember that split and strip are what you use to manipulate the inputs you read, to get rid of extra white characters, to remove, separators of whatever sort, whether the commas, semicolons, whatever. We're going to use the first approach in our solution. We're just going to read in all those words because there's really not that many of them. So here's my first attempt at read words. It takes a file name, which by default is words.dat. There's my doc string, reads in a file consisting of 1 word per line, returns a list of words, tells you what it does. I open the file for read. Notice that here I'm using the argument name file name, which by default is words.dat, but can be any file you specify. I open it for read access only. I'm going to read in the whole list all at once, and I'm going to use the split method to split by whitespace, which includes the carriage return, all in one step. So W now is my word list. I clean up after myself. I'm going to print some nice little feedback for the user so they don't get bored, and then I'm going to return W, and that's all there is to it. I can try this function. When I say W equals read words, defaults to words.dat, it comes back and said, hey, I read 57 words. This is a print. Notice this is a print. It's not the value that read words return. Read words returns a list of words. And the assignment makes sure that you don't see that list of words, because assignment always returns none. This is just for the user to know that the right thing happened. Print is not the same as return. The assignment returns none. Also, I want to note that this print string is really ugly. I have to take the length of W, I have to convert it to a string, and I concatenate it with a space and then words read. Good Lord. Producing good output like this is nasty, as you found out, some of you have found out in your show table and so on. Fortunately, there's a better way to do this. Unfortunately, we're going to wait till Friday to find out what it is, but I'll give you a little hint. And we're going to use the format directive for strings, which is a method of string type. But you don't need to know that today. We'll do it after the exam. That's it for today. The TAs will be watching CATSA. I've asked them to take turns to make sure that questions are answered in a timely way. Don't forget Lab 6 tomorrow. Don't forget the exam on Wednesday. I'll see you Friday. I'll be out of town, so I probably won't be answering email before then, before I get back. Take care.